丈夫かな。
ああ、
はい。じゃあ時間ですかね。Okay, so we start the second session of second talk of today's morning session. So the speaker is Shinichi Kobayashi from Kyushu University, and the title is Local Units and Root Numbers in Anticyclotomic Extensions at Inert Primes. So please start.
Thank you. First of all, I would like to thank organizers for giving me the opportunity to talk in this great conference. And I was a student of Takeshi almost 20 years ago. In the master course, I studied local root numbers of elliptic curves influenced by Takeshi. And then I switched to study Iwasawa theory in the doctor course. And unfortunately, did not return to the ramification theory so far. But however, recently, root numbers come again in my research, fortunately, and which is the topic of my talk today. Actually, Takeshi has many students studying various topics in number theory. And as Professor Kato pointed out before his talk, Takeshi accepted various students and raised many mathematicians. I'm proud that I was his student, and it's my great pleasure to talk his 60th birthday conference here.
Thank you.
Okay. So let me start. So I suppose there are not many specialists of Iwasawa theory here. So let me start from the behavior of model value ranks in GP extension. So let E be an elliptic curve defined over a number field, and WE over F is the root number of E over F, the sign of functional equation. And we consider the GP extension of F. It's an infinite extension whose Galois group is isomorphic to GP. So there is a unique intermediate field of degree p to the power n, Fn. It is called nth layer. And we are interested in the behavior model value rank of Fn and by varying n. And and then there are I introduced two examples of GP extension. One is a cyclotomic GP extension, and it lives in the cyclotomic field. And the other example is anticyclotomic GP extension of imaginary quadratic field K. I fix notation. K is always imaginary quadratic field in my talk. The anticyclotomic GP extension is characterized by the following equivalent property. First, so Galois group of K over K, so complex conjugate acts on the Galois group of GP extension non-trivially. And actually, anticyclotomic GP extension is Galois over Q, and the Galois group is dihedral over Q, and it lives in class field of conductor P power. Yeah, and yeah, anticyclotomic extension is important because it arises from, for example, CM points, CM points of modular curve and deformation space of abelian varieties or limited formal groups. So Iwasawa theory for anticyclotomic Iwasawa theory has a geometric aspect. And now I recall Mazur's result. So suppose E over F has a good ordinary reduction. The ordinary condition is very important at all places over P. And then under mild assumption, there exist integers A and E such that the rank of model Bay group is described as follows. Yeah. So the rank is A times P to the power N plus E for sufficiently large N. So individual model Bay group behaves irregularly, but as a system, as a family, yeah, it behaves very well. And if so, we want to know A explicitly. In general, it is very difficult to determine A, but if F is Q and F infinity over F is cyclotomic GP extension, then it is known that A is equal to 0 by Kato law. So the model Bay group is bounded for N. And now we consider the anticyclotomic case. So F is K, imaginary quadratic field. And for simplicity, maybe we assume is defined over Q. And we consider the anticyclotomic GP extension. Then it is like this. So it's different depending on E has CM by the K. So CM. So Mazur calls that this case, the second case, the exceptional case. So E has CM by the fixed K. We are considering the anticyclotomic GP extension. So the first one is called generic. So it may have CM, but not by K, but different field, different imaginary quadratic field, or it has no CM. So in the generic case, yeah, A is 0 over 1, depending on the root number over K. In this case, so root -1 case, actually, so we have a lot of point of infinite order. And they come from Kiguna point, essentially. The second case, root number over K is always 1 because it has CM by K. So the rank must be even. So root number over K is always even, but root number over Q may not be +1. So depending on the root number over Q, it is 0 or 2. Yeah, this is the exceptional case. And yeah, so in the exceptional case, we cannot relate Higuna point directly. So, but we use Higuna point to determine A here. But we indirectly use Higuna point. And now we consider good supersingular case. Good supersingular case is actually similar, except the exceptional case here. Yeah, non-exceptional, so generic case, the behavior model Bay rank is similar. In the supersingular case is similar to the ordinary case. But the order of Tate-Shaffer-Fitch group, the behavior of the order of Tate-Shaffer-Fitch group is different. In my talk, yeah, I talk about this exceptional case, so exceptional supersingular case. So from now on, I assume is defined over Q and complex multiplication by K. Actually, Q curve is okay, but for simplicity, I always assume is defined over Q. And P is prime greater than 5 and inert in K. So, and good for E. So E automatically has the supersingular reduction. And now the behavior model rank is like this. Yeah. So it is a little bit strange. So depending on root number, so the parity of n. We have new points of infinite over order in every other layer. So for example, if root number is +1, then for even n, we have a new point. For odd n, we don't have new point. So the behavior is a little bit strange. Actually, yeah, more precisely, for anticyclotomic character chi, conductor p to the power m, we have a new point in the chi part of the model value group, depending on the root number. So counting the number of chi, we have such number. Yeah, and yeah, of course, there's an analytic counterpart of this theory, of this phenomenon. Now consider L function. So let phi be the Hecke character associated to E. Then we have the following, decomposition formula of L function. Yeah, and each L function has the functional equation like this. So for character chi of conductor p to the power m, the functional equation is like this. The point is that anticyclotomic implies certain self-duality. So we have here the same character appears. And so the root number is always ±1 for any chi. And the root number is this. So the root number of phi e times chi is -1 to the power m times the root number of the bottom. So depending on the parity of m, root number changes. And Rory showed that for sufficiently large m, he determines the actual order of a function. So the order is 0 or 1, depending on the parity. So it depends on the root number. If the root number is +1, then order is 0 in general. Yeah, if the root number is -1, it's order is 1. And we can deduce Greenberg's formula by using Gross-Zagier formula from Rory's result. So this is really interesting film, I think. And Iwasawa, so Rubin envisioned Iwasawa theory reflecting such phenomena in this paper. And Iwasawa theory of elliptic curves at the ordinary primes or equivalently at split primes well developed. And it is a success and ideal model in Iwasawa theory. However, at the inert primes, the theory is still not completely satisfactory. Of course, there are important progress by Andrea Toyota recently, but I think it is still not completely satisfactory. In this paper, Rubin proposed a beautiful Iwasawa theory of CM elliptic curves for the anticyclotomic extension at the inert primes. The theory provides a good periodic L-function in non-cyclotomic and non-Punchkin setting. So, and here, let me, before I explaining his theory, Rubin's theory, let me talk about a memory of Takeshi's seminar. In the arithmetic geometry group of Tokyo University, there is a long traditional seminar we called Saito seminar. At least in my generation, the seminar was called so. And in the seminar, doctor course student or PhD student choose one paper he or she is interested in and must give a 90 minutes talk. Sometimes I remember it becomes 3 hours or 4 hours in front of Takeshi, and together with Shuji Saito, Takeshi Tsuji, in my generation also Kazuya Kato was there, and also organizer of this conference, Shiho, Banai, Uchiai. So for a student like me, it was really high pressure seminar. And just after writing my thesis, I gave a talk on this Rubin's paper here in the Saito seminar. Maybe no one remember, but I gave a talk on this paper in Takeshi's seminar. So today's talk is a continuation of season 2 of my talk, the 20 years ago. And the main content of this paper is conjecture, actually, on a structure of the Iwasawa module of local unit in the anticyclotomic GP extension. And Rubin gave partial evidence on his conjecture in this paper by using elliptic unit, global object elliptic unit, inner points. Yeah. Also, his conjecture is local, actually local. It's a kind of Perandue theory, yeah. But he used global object like elliptic units, inner points to give evidence. And unfortunately, in the Saito seminar, I could not give proof of his conjecture. But now, together with Burungale and K, I could solve his conjecture. And it is my great pleasure to explain it in this conference. Okay, so Rubin's conjecture is local. So I start the setting again, local setting. So let phi be the unramified quadratic field of QP with integer ring O. So phi is completion of K before at P. And psi infinity is a local anticyclotomic GP extension of phi. I use phi infinity as GP2 extension. So psi infinity is the local anticyclotomic GP extension in my talk. And let T be the Tate module actually of E, but so I want to state Rubin's conjecture purely locally. So we fix the Rubin Tate formal group F over O of height 2 with parameter minus P. And T is the periodic Tate module of F. So actually it is a Tate module of E hat. And big T is fat T. Big T is T tensor lambda. So Iwasawa theoretic anticyclotomic deformation of the Tate module. Lambda is anticyclotomic Iwasawa algebra. And we consider finite character groups, and we divide it into two. So gamma plus is finite character of conductor p to the power, even power of p. And gamma minus is characters of auto p power conductor. And then we consider dual exponential map. So for chi, we define delta chi be chi part of dual exponential map. So we have canon, we evaluate by chi, and then we take dual exponential map of this representation. V is T tensor QP, and so actually delta x is a dual exponential map of V tensor chi. And according to Rubin, we define some subgroup H1 plus minus like T. So this is actually Iwasawa homology like this, and by Shapiro's lemma, and we define H1 plus is element x whose image by dual exponential map is 0 for chi in gamma minus. So the sign is different. It is correct. And so note that if we consider x as a system of finite Galois homology groups, then delta chi x is equal to 0 if and only if xn comes from chi part of the local model Bailey group. Because delta chi is dual exponential map, the kernel is H1F. Yeah, H1F is a rational point. So we consider such a strange subgroup. And Rubin shows that this group is rank one, free of rank one as a lambda module, and there's no intersection. And he conjectures the following. This is the Rubin's conjecture. Yes. So the local Iwasawa homology is divided into plus part and minus part. And recently we proved it. And this is a main theorem of my talk. And maybe you wonder why we expect such a strange decomposition. My feeling is that it may be a kind of a local version of equivalent BST or parity conjecture. We saw the model behavior in connection with the global root number before, and the global root number changes depending on the parity of the exponent of conductor. But precisely speaking, actually, the local root number to P changes depending on the parity. Actually, so gamma, so this index is actually the index of local root number. Yeah. And if we believe local version of parity conjecture, maybe if the local root number is -1, we expect some local point. So maybe some local point will be related. So it's kind of BS local parity or BST equivalent version. Yeah, it's my feeling. Yeah, so I think there is also an intrinsic relation between Rubin's conjecture and Kato's local epsilon conjecture. Kato's local epsilon conjecture is equivalent epsilon conjecture. And in fact, we can prove Kato's local epsilon conjecture in our setting by using this main theorem. And it may be, but in commutative case. So in our case, anticyclotomic GP extension is dihedral over QP. So it's a little bit non-commutative. So maybe Rubin's conjecture, maybe something non-commutative Kato, local epsilon, Kato Fukaya's local epsilon conjecture. Anyway, yeah. Now, actually, Rubin stated this decomposition in terms of local unit. So we write this more down to earth language. So let UN be the group of principal units in the division field of for the formal group. Maybe this should be. And so this is a this is divided in GP2 extension. So, and yeah, so big U is the limit of the limit of UN. Limit is taken by norms. So this is usual Iwasawa theoretic object. And two variable Iwasawa algebra acts on U. And then we consider the anticyclotomic projection of U. So we twist a little bit by T, then we take anticyclotomic projection. And then standard argument shows that H1 phi T, big T, is isomorphic to this local unit. So Iwasawa algebra, Iwasawa module local unit. And yeah, so we define V star plus minus as the inverse image of H1 plus minus by this map. Of course, we need to describe delta chi dual exponential map in terms of local units. And then this is so there's explicit description of delta chi. This is explicit reciprocity law by Wiles. Yeah, Coleman power series. So actually, if we have norm compatible system of local units, then consider Coleman power series associated to U, then take Kurzweil's derivative. It gives delta chi. This is Wiles explicit reciprocity law. And we have elliptic unit in actually elliptic unit lives in here, but we can consider we twist elliptic unit and project to V star. Then we have a system of consistent constructed by elliptic unit such that the image by the dual exponential map is L value, like this. And so according to the parity, so this if the parity root number of this character is -1, then L value forced to vanish. So this is 0, if depending on the parity of conductor. So one finds that the elliptic unit lives in V star epsilon. Yeah, epsilon is root number over Q. So depending on the parity, global root number, elliptic unit lives 1 over V plus minus. And yeah, now Rubin defined periodic L-function. So we fix a generate. So Rubin showed this is lambda free of lambda 1. So there's generator. So we fix generator, and elliptic unit lives here in here. So there's an element of lambda such that it's a ratio of elliptic unit and the fixed generator. This is Rubin's periodic function, and by using Rubin's conjecture, we proved we can we can consider Coleman map or Perrin map easily. For example, so yes, by Rubin's conjecture, we have such projection by Rubin's conjecture, and this is isomorphic to lambda by fixed generator. So, and yeah, elliptic unit is set into Rubin's periodic function. So by using Rubin's conjecture, we can construct periodic function as the image of elliptic unit. Like one. And now I explain the interpolation formula of Rubin's periodic function. So by definition, Rubin's periodic function has this interpolation formula for chi in gamma epsilon. Yeah. So, and yeah, this means that we eliminate P-Euler factor from L function. And yeah, actually, so the delta chi of V epsilon is non-zero. This is non-trivial consequence of Rubin's conjecture. And yeah, so it's a kind of periodic period and an analog of Gauss sum, I think. And we have general conjecture. So in the cyclotomic deformation, we have general conjecture of periodic L function. And at least conjecturally, we can guess the interpolation formula of periodic L function. But I think non-cyclotomic, non-punchy skin case, yeah, actually we don't know explicit interpolation formula of periodic L function, even conjecturally. I think one reason is that we don't know what invariant appears in the interpolation formula. So, for example, Gauss. So in the cyclotomic case, Gauss sum appears, but of course, Gauss sum is cyclotomic object. So it will not appear in general non-cyclotomic case. And in some sense, Rubin's, yeah. So this is, so delta is a kind of so non-cyclotomic analog of Gauss sum period. It is a mysterious object. And Rubin asked the periodic variation of this invariant. And we can answer, yeah, also answer his question now. And yeah, actually, this is a computation of the periodic variation of Gauss sum. But so, of course, classically, for classical Gauss sum, it is really easy to determine the variation of Gauss sum because Gauss sum is defined very explicitly. But here, so for example, for anticyclotomic case, we don't know good system of uniformizer like cyclotomic units. So there's no explicit way to define this. So I think explicit computation is difficult. But we use ramification theory like in classical ramification theory, like Sales book. We look the action of higher ramification group, and then we can determine this value. And then, as an application, we have such a symptomatic formula of L value, variation of the P L value. So this is integral object. So the quotient should be integral object. And we know the variation delta, so we can determine the variation of L the variation of L value. The answer is like this. So yeah, this is the variation of P that comes from like variation of period, and this value comes from some part of this invariant. Yeah, actually, yeah. So sorry, I state precisely. So suppose epsilon, so root number is +1. We also have the similar formula for epsilon -1. So I state only +1 case. Then there is Iwasawa invariant lambda mu integer, and for chi, so epsilon is +1. So for chi, we have the variation is like this. Yeah, for sufficiently even yeah, conductor is p to the power n. Of course, if we can show that so if the bottom is not divisible by p, then lambda mu should be 0. So we have the formula for all n, yeah, with lambda equals 0, mu equals 0. And this is one application of one theory. And now, so this is the interpolation formula for gamma epsilon. So Rubin also asked the interpolation formula for gamma minus epsilon. Yeah, in this case, yeah, root number is -1, so L value is 0. And yeah, since Rubin's periodic L function lives in lambda, so it only has finitely many 0. So for such character, yeah, Rubin's periodic L function cannot interpolate L value because then there are infinitely many 0, so L must be to 0. So so if the L value is 0, then by BSD conjecture we expect local point P in the chi part of the model value group, and it is natural to guess that Rubin's periodic L function interpolates log of such a rational point. Yeah, and this is Rubin's guess, and we can answer his question too. First, I state the interpolation formula for the trivial character. Yeah, so suppose that root number is -1. Then, yeah, there is rational point P, E of Q, such that so Rubin's periodic L function has 0 at trivial character if and only if P is non-torsion, and if and only if the complex order of L function, and so analytic rank is 1. So P is like something like Higgs point. And the second property is that if P is non-torsion, then we have following certain periodic Gross-Zagier formula. So the value, so the missing interpolation, the missing value is like this. So U is 1 or 2, so this is interpolation factor. And yeah, this is the rational point, log of rational point, square of log. And here is a complex L value. The very complex L value appear. Yeah, and we know that V0 minus, it is the bottom layer of V minus, and by definition, delta minus is killed by dual exponential map, so it defines the local point of. So we can consider the log such local point. This is kind of Gross-Zagier formula. Actually, we use proof-realized Gross-Zagier formula at supersenior prime, and also we need Kato's zeta element. So we need a lot of heavy tools. And P is constructed by auxiliary Higna point. Note that, our E does not satisfy Higna condition because root number is always +1 over K. So Higna, Higna point. So canonical Higna point does not exist canonically. So we take another imaginary quadratic field satisfying Higna condition and consider auxiliary Higna point to prove this. And the right-hand side of B is independent of choice of P. So if we choose another generator, this term kills the ambiguity. And this is anticyclotomic analog of the periodic Bayesian formula. This is a certain periodic regulator, and this is the value of complex regulator. And there's ambiguity for each terms, but if we consider some ratio of periodic regulator, complex regulator, the ambiguity disappears, and such value can be should be interpolated by periodic L-function. It's a philosophy of periodic Bayesian conjecture by Perrin-Liu. So this is a kind of analog, anticyclotomic analog formula. And now I consider non-trivial character of gamma minus epsilon. We have the in this case, if for general characters, the result is not so satisfactory. For such chi, there's a rational point in the Selma group, not in the model Bay group, but in the Selma group, such that the value of periodic function at such chi is written as follows. So actually log of the rational point, point in Selma group. And if the analytic rank is 1, then by Gross-Zagier equilibrium, we know SHA is fine. We know the finite SHA, so Z chi lives in the model Bayes group, but with tensor QP. This is really important. So we cannot expect Z chi lives in here. So there's some transcendental part. To eliminate such transcendental part, we need periodic Gross-Zagier formula. If we use this formula and periodic Gross-Zagier formula, if it exists, then we have final formula like this. So this case is P lives in true model Bay group and the log square. So the formula is a little bit different. And if we put, if we have periodic Gross-Zagi formula to bat primes, then we can deduce from theorem 3 to a similar formula. Theorem 2. And looking this theorem, it is this interpolation formula. It may be it may be natural to expect that periodic BSD conjecture in this setting, like this. And so there's extra +1 because of the root number here. And we can prove the inequality by using Iwasawa main conjecture in terms of Rubin's periodic function. This is classical analog of periodic BSD conjecture by Kato. And I now state Iwasawa main conjecture in terms of Rubin's periodic function. Of course, we have Iwasawa main conjecture in terms of elliptic units by Rubin. But to obtain such a result, it is convenient to formulate the Iwasawa main conjecture in terms of periodic function. Agbur Howard have defined around 2003 or 4, yes, a signed Selma group. It is anticyclotomic analog of the Selma group I defined in my thesis. By using local condition H1 plus minus. And Agbur Howard proved that Selma group minus epsilon is lambda quotient. Plus epsilon has lambda, free lambda rank 1, but minus epsilon is finitely generated and lambda quotient. And the characteristic ideal is generated by Rubin's periodic function. But Agbur Howard assumed Rubin's conjecture. Now, we solved Rubin's conjecture. So the proof is completed. And as an application, together with theorem 2 for the interpolation formula for the trivial character, we can prove weak P converse theorem. So let EQ be over Q CM elliptic curve and good supersingular reduction at P. And so it's converse of Gross-Zagi Kobayashi theorem. So we first assume rank is 1 and the Tetsch-Farevich group is finite. Then analytic rank 1 and then analytic rank of L function is 1. So this is Gross-Zagi Kobayashi. So it is converse of Gross-Zagi formula. And now, so I have 10 minutes. So I explain the proof of our proof of Rubin's conjecture. Rubin has shown that actually, so V plus minus is of lambda rank 1, and there's no non-trivial intersection, and the conjecture is a decomposition. And our strategy of the proof is that we construct a candidate, a generator of V plus minus star. More precisely, construct an element whose bottom term is P indivisible. Then by Nakayama's lemma or something, commutative algebra, simple calculation, cohomology group implies the decomposition. So keys construct generate candidate of generator. And this is actually not our strategy, but Rubin's strategy. Rubin systematically constructed elements in V plus minus star via global arithmetic by namely elliptic units, Figma points, and proved freeness. And he also showed that his conjecture is true if one of his elements he constructed by global methods has the p-individual property. And he numerically checked in most cases it has p-individual property. Yeah. And we followed his strategy, but modified his construction to get more elements for which the p-individuality may be studied via local global tools. So actually, so Rubin only used global object like elliptic units and Figma point. And for such global invariance, it is very hard to show p-individuality result in general. So actually, we use some local theory and we define some local object. Then it is not difficult to show p-individuality. And now I explain precisely. So plus case, so V plus, for V plus, the p-individuality is in this form. So yeah, this is the image of dual exponential map. And yeah, if there's no plus, yeah, it is equal. So to show yeah, we expect that even for V plus, the inclusion must be equal. Then, yeah, this is the PDB property of V0 plus. And in minus case, V minus case, actually, V minus star is killed by bottom dual exponential map by definition. So this element defines, so the bottom element defines local point of formal group. And we expect, yeah, this should be equal. Yeah. And this is a purely local statement. So yeah, it is natural to prove it by local tools like phi gamma theory. Actually, for cyclotomic case, cyclotomic variation, we can consider similar problem. But in this case, we can solve it by Honda's theory, for example. Yeah, just like in my thesis. But currently, phi gamma theory for Rubin Kato group is, I think, not so well developed, and I don't know it is available to show such integral property. Anyway, we could not use sophisticated local theory. Of course, I tried, but okay. So. Anyway, we use some global methods. The plus case. Now I explain the plus case. Now we take an elliptic curve A. So note that this is different from E before. So actually we vary A. So A is CM elliptic curve, CM by K prime. Imaginary quadratic field, a good supersymmetry at P. So the completion at P of K prime is phi, and P splits completely in the Hilbert class field in our case. So locally, so the formal group of A is isomorphic to F, our fixed limited formal group. And a natural idea is to use a system of elliptic unit defined by, constructed by elliptic unit of A, because then it's an image. Yeah, we compute for such element. We compute the image of dual exponential by global L value. So if we know the p indivisibility of such value, then we have the plus conjecture plus local indivisibility. But yeah. This problem is still open problem, so we don't know such a exist. Yeah, maybe exists, surely exists, but yeah, we cannot prove. And our solution is to use finished result. Yeah, finished shows that if we take some finite character eta, then the L value is p indivisible. So we extend a framework of Rubin little bit and to include elliptic unit associated to eta, so twist by eta, and then yeah, we consider such element interpolating finished L value. Yeah, this is a proof of the p indivisible result for plus case. And then now I explain the minus case. Yeah. The minus case fix an elliptic curve E. So different from so before, yeah, we vary A, and the formal group is fixed. Yeah, yeah. First we fixed the isomorphism E and vary A. Yeah, the situation is similar. Yeah, we fix elliptic curve E, CM by K as before. And by the local duality, we can show that the p indivisibility for V minus is equivalent to the existence of a family of local points satisfying such relation. And the bottom layer is p indivisible. And this is simple, yeah, calculation. So, it pair. And so, yeah, in the cyclotomic case, I constructed, yeah, such system of local points by using Honda's theory. Yeah, but as I said before, Perrin theory, Honda's theory is equivalent, almost equivalent to Perrin theory, and yeah, fine. So it is happy if we can use phi gamma theory to construct such point, but for anticyclotomic case, yeah, I don't know. Yeah, so I don't know how to. I didn't know how to solve it in the Saito seminar. Yeah, and now, yeah, yeah. And Rubin considered like this. Natural idea is to use Hegna point. Hegna point is global object, but satisfies such relations. This is a relation of Euler system relation of Hegna point. And so Rubin considered Hegna point and modular parameterization and send Hegna point to E, and then he has such local points, but to show the p indivisibility result is very hard. Yeah, for example, yeah, I think it is not accessible even now. Recently, there is work by Wei Chan for the p indivisibility in global model Bay group. So Hegna point criterion Hegna point is p indivisible in global model Bay group or not. And there's also a result of gross person. Yeah, it says it is local. It describes local p indivisibility of Hegna point in L-adic field. So L not equal to p. So there are such results, but there's no result in this set. Yeah. And our solution, so I have 1 minute. So our solution is use formal CM points. Yeah, it's not a global object. It's a hybrid object. So the elliptic curve A over local field has formal CM if the endomorphism group of the formal group is bigger than GP. For example, any elliptic curve defined over QP with AP equals 0 has formal CM. So A might not have CM globally, but so locally it behaves like CM elliptic curve. And we use Gross's canonical lift. So starting from such A, we can construct a family of formal CM elliptic curves. So it's a quasi-canonical lift of the fiber of A. So actually, Gross's theory is a theory for formal group, but yeah, we can have elliptic curve. We have elliptic curve over ring class field. So now we consider so points so correspond to formal CM elliptic curve in global modular curve, and then this system satisfies this norm relation by looking Hecke operator. And this is purely local, this is local object. So easier than, so treat easier than treat. So for example, yeah, for modular parameterization is étale except finite many points. So in most of points, yeah, locally this is isomorphic. So we can construct many p individual elements here, and such curve exists then. So many such elliptic curves. So with continuous cardinality. So we have a lot of points. So we can show the PDT for such points, such formal points. Yes. So yeah, yeah, I stop here. Thank you very much.
Okay, thank you very much for nice talk. So maybe any questions from Professor Saito?
Yeah, so thank you very much for nice lecture. And I think you have something to say on this local epsilon conjecture.
Yeah, but yeah, it's I made slide, but basically it's just a reminder. So yeah, I explained. I explained. Yeah, Kato's local epsilon conjecture. And yeah, Kato's. So Kato's epsilon conjecture is shown for such cases. Yeah. Especially Nakamura's result is very strong. Nakamura's logic Jacinto is that is very strong. So almost so for all rank 2 case it's proved. And our case is not commutative case. Our case is like this. So this is rank 2. So our case is already proved by Nakamura Jacinto. But we can give another transparent. Yeah, actually Nakamura used periodic Lagrange heavily. So it really heavily depends on periodic Lagrange GL2QP. So yeah, our construction is transparent and may shed some light on the case of general cells dual deformation. And it may be interesting to consider non-commutative case too, because anticyclotomic station dihedral.
Yeah, And so your plus minus construction is always mysterious to me. So I wonder how maybe you can tell me some heuristic reason why it is related to the sign of the epsilon factor root number.
Yeah.
How this n parity of n is related to
Yes, yes. Yeah, this is one of the reasons I consider Kato's local epsilon conjecture. If I consider the Kato's local epsilon conjecture in this case, then I hope that I find explicitly some idea to some relation, explicit relation between local root number and plus minus construction. But so far we could prove Kato's local epsilon conjecture, but I think Rubin's conjecture is stronger than Kato's local epsilon conjecture. Of course, and information is information loss. So maybe if we want to consider non-commutative case, maybe we can see nice relation between local root number and plus minus construction. Maybe, I hope.
Yeah, thank you very much. So that is from me.
Okay. So any other questions from other participants? Okay.
栗原さん。
あれ解除されない。あれされた。あれおかしいな。
まだされてないですね。
なんか解除できない。
栗原さんまだミュートが解除になってないです。
sorry. So now, can you hear me?
はい。
Okay, so thank you very much for beautiful theorems. So you began with the behavior of the growth of the model Bay groups, and such a behaviors can be explained by something like auxiliary Higner points or some z-chi you introduced during the lecture was some kind of such kind of object. That's first question.
Sorry.
Some kind of Higner points or you at first you explained the growth of the model Bay groups. Twice of something or
actually we can, for example, we can show Greenberg's formula by using z-chi, for example.
No. My question is some kind of some geometric objects.
In my case, in my case, there's no. We use auxiliary Higner points, but there's no canonical choice of Higner point. Actually, for example, to show this, I used Higner point. We take another imaginary quadratic L satisfying Higner condition. The K does not satisfy Higner condition. So
here, so in theorem 3, you said at first z-chi is a Selma group, but finally it's a generator of the model Bay. So can you show the finiteness of the Tate-Shafarevich?
In this case, yes, by using the K.
I see. Certainly, And this z-chi comes from some auxiliary Higner points, you said. Is this correct?
But indirectly, counting the dimensions. Actually, so in this case, so in the trivial character case, we have periodic Gross-Zaghi formula. So we can say more about z chi, but yeah, in this case, yeah. We also used Kato's element. Yeah, yeah, this is constructed from elliptic units, but we relate it to Kato's element, etc. Yeah.
And +1 you said, so if chi is in a gamma minus epsilon, then rank is order +1, you said. After the theorem 3, yeah, maybe after
this.
Yeah. Such +1 can be also explained from this some kind of modification of Higner points or something. So that was another. That was my question.
Yeah. Actually, yeah, there's no canonical way to construct rational point corresponding to this one. Yeah, of course, candidate is constructed periodically.
Yes.
Yeah, but so for as a true global object, yeah, we use auxiliary Higner points. So there's no canonical rational point.
Thank you very much.
And any other questions? So if you have some question, please raise your hand. Maybe not.
Maybe not. Then can I ask one more question?
Okay.
Okay. Then, so in a local theory, you consider the anticyclotomic ZP extension, but can you get a theory for ZP cross ZP extension in this situation? Local theory, I mean.
Yeah, two variable theory.
Yeah, two variable. Yes.
I think, yeah, it's not something like this. Yeah, self-duality is important.
I see.
Maybe we need huge denominators. Yeah.
So to get such theory, you need something more then.
Yeah. In the anti-some cases, very special and can very nice periodic function. But for example, two variable periodic function at inert prime is very strange. Very, yeah.
Thank you very much. Thank you very much.
Okay, so maybe let's thank the speaker again. So thank you very much.
Thank you very much.
So we will resume at 5 p.m., but now we have an announcement from Banai. So
yeah, okay. I'm sorry, I'm the Gather Town person, so I make an announcement about Gather Town. So the